Hey there guys, this is the third and final part of Edexcel's A Level Maths Sample Assessment Materials, Paper 1, Pure Maths. Here we're doing question 11 to 15. Let's go. Okay, question 11. So, an archer shoots an arrow. The height h meters of the arrow is modelled by the formula h is 1.8 at 0.4d minus 0.002d squared, where d is greater than or equal to 0 and d is the horizontal distance in meters from the archer. Given that the arrow travels in a vertical plane until it hits the ground, we want to find the horizontal distance travelled by the arrow as given by the model. So, let's think about this. When the arrow hits the ground, the height of the arrow is 0 meters. So we want to set this quadratic equal to 0 and solve. So, for part A, we are setting the quadratic equal to 0. So I'm going to write this as minus 0.002 d squared and 0.4d add 1.8 is equal to 0. Now the method that I'm going to use here is the quadratic formula. We can get straight to the answer. So A is minus 0.002, B is 0.4, and C is 1.8. So, by the quadratic formula, D is equal to minus 0.4 plus or minus the square root of 0.4 squared and then minus 4 times minus 0.002 times 1.8 and then that's all over 2a, so minus 0.004. So this would lead us to two possible answers. One though is negative and one is positive. Given that D is a length, a negative answer doesn't make sense. So the only answer that we're interested in, if we go to the nearest meter, it would be D is equal to 204 meters. Cool. Part B asks us, with reference to the model, interpret the constant 1.8. So, what's going to happen when t is equal to 0, so the distance of the arrow from the archer is 0, the archer is holding the arrow. In terms of the model, when t is equal to 0, well, 0.4d and minus 0.002d squared are going to disappear. So when d equals 0, h equals 1.8. So we would say it's the initial height of the arrow. Cool. Okay, now part C wants us to write 1.8 at 0.4d minus 0.002d squared in the form a minus b lots of d minus c squared, where a, b and c are constants to be found. So this is completed square form, so we want to complete the square. So, the first problem that we have is that we don't have a single positive d squared term. So what we need to do is divide everything through by minus 0.002, plonking that on the outside of a set of brackets. So we're taking out a factor of minus 0.002. So, if we do that, we get minus 0.002 lots of, and we now divide everything by minus 0.002. So, minus 0.002d squared divided by it is d squared. 0.4d divided by minus 0.002 is minus 200d. And then 1.8 divided by it is 900, minus 900. Okay, so now inside of that bracket we can complete the square as normal. So we've got minus 0.02 lots of, well, if we complete the square, we're going to have d minus 100 squared. Now on the outside, we've already got minus 900. And then we also have to subtract 100 squared. So 100 squared is 10,000. Alright, so we've got minus 0.002 times d minus 100 squared minus 10,900. Okay, so we now need to let that factor of minus 0.002 back inside. So all it can do to the squared bracket is sit on the outside, multiplying it. But then it is going to multiply the minus 10,900, which gives us 21.8. So, in the form that they wanted this, we can write this as 21.8 minus 0.002 times d minus 100 squared. So, for a bit of bonus information here, remember the whole point of completing the square is to find a maximum or a minimum of a quadratic. So what we've done here by completing the square, remember this arrow is going to be going up to a maximum point and then it's going to go down until it hits the ground. So what completing the square here allows us to do is work out the maximum height of the arrow and the distance d from the archer that happens. So the maximum value, or the maximum height, is going to be this constant 21.8 at the start, and that's going to happen when this squared bracket is equal to 0. So the max height of the arrow is 21.8 meters, and that is going to happen when d is equal to 100. So then inside of that bracket, 100 minus 100 cancels out. So the maximum height is 21.8 meters, which happens when d is equal to 100. So, we weren't asked to do that, I just thought it's nice to chuck the extra info. Okay, so it turns out what we've just done is going to help us for the final part of this question. So, it is decided the model needs to be adapted for a different archer. The adapted model is h equals 2.1 add 0.4d minus 0.002d squared. So for the adapted model, we want to find the maximum height the arrow will reach and the distance from the archer that this occurs. So this adapted model is so close to the original model. The only thing that's changed is here we have 2.1, whereas in the original model we had 1.8. The rest of it is exactly the same. So all that we've done here is added 0.3 to our original model. So this model is a translation up by 0.3 of the original model. So we've already worked out the maximum height in the original model, and that was 21.8. So for the adapted model, the maximum height is 21.8 add 0.3. So that is 22.1 meters. Now, given that this is only a translation up by 0.3, nothing horizontally is affected at this maximum point. So, we already worked out where the maximum occurs for the original model. That was at d equals 100. So the maximum still occurs at d equals 100. So the answer is again just d equals 100 meters from the archer. Okay, question 12. So in a controlled experiment, the number of microbes n present in a culture t days after the experiment started were counted. N and t are expected to satisfy a relationship of the form n equals a times t to the power of b, where a and b are constants. Part A asks us to show that the relationship can be expressed in the form log 10 of n is equal to m log 10 of t plus c, where we want to give m and c in terms of a and b. So we're starting off n is equal to a times t to the power of b. Now, if we log both sides, we get log base 10 of n is log base 10 of a t to the b. By the rules of logs, over on the right, log 10 of a times t to the b can be split up into, well, I'll show you. So we've got log 10 of n. So we can split this log up into a log of log base 10 of t to the b, add log base 10 of a. And then, again, by the rules of logs, we can write log 10 of t to the power of b as b log 10 of t. So, finally, we can write this as log 10 of n is equal to b log 10 of t, add log base 10 of a. There we go. Okay, so now we got this graph here, which shows the best line plotted for values of log base 10 of n going up the side and log base 10 of t going along the bottom. So part B says, using the information provided, estimate the number of microbes present in the culture 3 days after the start of the experiment. So we are going to need to pair information on this graph with the equation here that we just worked out. Now this equation is comparable to y equals mx plus c. So what are we going to need to do then? Well, we need to work out the values of b and a. So b, because that's multiplying the log base 10 of t, and t here is the equivalent of our x variable, b is the gradient of the line, and log a, or log base 10 of a, is our constant term, or our y-intercept. So log base 10 of a is the constant, or the y-intercept term. Now, the reason for that is because it's not multiplying a t at all. Log base 10 of a, in terms of t, is just a constant. So a is going to be the easiest one for us to work out. So let's do that first. So if we go back to the graph, we want the value of the y-intercept, which is this point here. Now, I reckon we would be alright using the y-intercept here is 1.8. It's only just above, but I think we would be fine. Saying that, log base 10 of a is equal to 1.8. Now, we want to work out here then what a is. So, if log base 10 of a is 1.8, then we know 10 to the power 1.8 is equal to a. So if you chuck that in your calculator, we will get a is 63. So now to find b, remember b is the gradient of the straight line. So let's go back. So I picked these 2 points here, which are roughly 0, 1.8 and 0.2, 2.25. So remember, gradient is the difference in y over the difference in x. So our gradient here is 2.25 minus 1.8 divided by 0.2 minus 0. So that gives us that the gradient is equal to 0.45 divided by 0.2. Now if you put that into a calculator, we get the gradient is 2.25. So the value of B is 2.25 using the numbers that I've used. So remember, what we're trying to do now is find n when t is equal to 3. So we could either use the logarithmic equation, or remember, this is also our model. So we're going to use this guy. So n is a times t to the power of b. So we now know a is 63. T is equal to 3. So we got 63 times 3 to the 2.25. And that gives us a value of 746. Now remember, with these types of questions, there isn't just one exact answer. The whole thing is based on estimating. The straight line is only a line of best fit, for example. So if you've got a slightly different answer, it might not necessarily be wrong, just something in this region, and you're golden. Okay, then part C asks us to explain why the information provided cannot reliably be used to estimate the day when the number of microbes in the culture first exceeds 1 million. Okay, so let's think about this then. So if n was equal to 1 million, remember our graph on the y-axis is log base 10 of n. So if we log both sides, log base 10 of n would equal 6. If n is 1 million, then 10 to the power of 6 would give us n, or 1 million. Now, our graph, or our data, only goes to, well, our last point over here was log base 10 of 4.5. So it doesn't go anywhere near log base 10 of 6. So we cannot assume that the model will hold indefinitely. So remember, log base 10 of 5 would be when n is 100,000. So a million is 10 times bigger than that. So we cannot assume that the model will hold as the population keeps growing. Okay, then part D asks us to explain or interpret the value A in the model. So, remember, n is equal to A times t to the power of b. So, for once here, A is not the initial value. Remember that t is the number of days that have passed since the start of the experiment. If t was equal to 0 here, then n would equal 0. So, what about when t is 1? So, when t is equal to 1, n would equal a. So 1 to the power of b, whatever b is, would just be 1. So a is the population after 1 day. Good times. Okay, question 13. So the curve C has parametric equations. X is 2 cos t and y is root 3 cos of 2t. For t between 0 and pi. Our first job here is to find dy by dx in terms of t. So, we need to first of all find dx by dt and dy by dt. So let's do that. So, dx by dt, well, if x is 2 cos t, that differentiates to minus -2 sine t, and dy by dt well, if y is root 3 cos of 2t, that is going to differentiate to -2 root 3 sine of 2t. So -2 root 3 sine of 2t. Okay. Now, dy by dx well, that's equal to dy by dt times dt over dx. So, we've got -2 root 3 sine of 2t over -2 sine t. Now there's a common factor there of -2, so dy by dx is equal to root 3 sine of 2t all over sine of t, which we could actually make a little bit nicer using a trig identity. So sine of 2t is 2 sine t cos t. So we can say this is 2 root 3 sine t cos t, and then that's all over sine t. So then there's a common factor of sine t. So finally we can say dy by dx is 2 root 3 cos of t. I think you would have got the marks for leaving it in terms of sine 2t and sine t, but I'm probably going to need this, so we might as well make it as simple as possible. Okay, for part B, the point P lies on C where t is 2 pi over 3, almost like a poem. The line L is the normal to C at point P, so it's the line perpendicular to the curve at this point. We want to show that an equation for L is 2x minus 2 root 3y minus 1 is equal to 0. Okay, good times. Right. Okay, so the first thing we need to do here is find the gradient of the line at this point. So we are indeed going to be using our derivative that we just worked out. So dy by dx was 2 root 3 cos of t. Right, so the gradient of C at P is the derivative evaluated at 2 pi over 3. So we can say that's dy of 2 pi over 3 over dx. So the value of dy over dx when t is equal to 2 pi over 3. So this is equal to 2 root 3 cos of 2 pi over 3. Now this is in radians, so put that in your calculator and we will get, well, cos of 2 pi over 3 is minus a half, so we've got here 2 root 3 times minus 1/2. So the 2's cancel out and we just get minus root 3. So if that's the gradient of the curve at this point, we can now get the gradient of the normal. So the gradient of the normal is minus 1 divided by minus root 3, which is 1 over root 3, which we could then rationalise the denominator of to get root 3 over 3. So we now know the gradient of the normal is root 3 over 3. So we can start smashing together the equation. So the equation of the normal, well, we know the gradient is root 3 over 3, so it's something to do with y equals root 3 over 3x plus c. So we now need to find the value of c. To do that, we substitute in the coordinates at this point. Now the bad news is that we don't know these coordinates, but we can work them up. Remember that we know x is 2 cos t, and t at this point is 2 pi over 3. So the x coordinate is going to be 2 cos of 2 pi over 3. Now 2 cos of 2 pi over 3 is just going to give us minus 1. And then for the y coordinate, well, we know y is root 3 cos of 2t. So y is root 3 cos of 4 pi over 3, which is minus root 3 over 2. So now we substitute those coordinates into y equals root 3 over 3x plus c to find the value of c. So we get minus root 3 over 2 is equal to root 3 over 3 times minus 1 is minus root 3 over 3 and then we got plus c. So we're now going to add root 3 over 3 to both sides, so we get c is equal to root 3 over 3 minus root 3 over 2 now that's going to give us minus root 3 over 6. Okay, so we can now say the equation of our line is y is equal to root 3 over 3x minus root 3 over 6. Now, obviously, that doesn't look anything like how we want it to, which is this bad boy here. So, we want 2x minus 2 root 3y minus 1 is equal to 0. So, we want everything on the same side. We just copy it, take it where we have more room. Okay, so first thing we're going to do is minus y from both sides. So that would give us root 3 over 3x minus y minus root 3 over 6 is equal to 0. Okay, now we can go through this and do it really carefully. So let's multiply through by 6. So that is going to give us 6 root 3 over 3x minus 6y minus root 3 is equal to 0. 6 root 3 over 3x cancels to 2 root 3x minus 6y minus root 3 is equal to 0. Now, if we divide through by root 3, we get 2x, which is good because we wanted that, minus 6y over root 3 minus 1 is equal to 0. So that minus 1 is also a good step because we wanted that. Okay, now if we rationalise the denominator on the y term, we've got 2x minus, 6 root 3y over 3 minus 1 is equal to 0. Final step, the 6 and the 3 cancel out on the y term, so we've got 2x minus 2 root 3y minus 1 is equal to 0, and that is exactly what we wanted to show. Good times. Okay, then part C tells us the line L intersects the curve C again at point Q. We want to find the exact coordinates of Q. Okay, so when lines or curves meet, they are equal. So that's what's happening when we solve simultaneous equations. We are finding the points where two lines meet. Now, here we don't have an equation for C in the form y equals some stuff to do with x. But what we do know about C are the parametric equations. So we know the equation for x and the equation for y in terms of t. So to find this other point where the normal hits the curve, we are going to substitute in x equals 2 cos t and y is root 3 cos 2t. We're going to substitute those into the equation we just found for our normal. So that is our way of setting the two equations equal to each other. So for part C then, so I keep forgetting x is 2 cos of t and y is root 3 cos of 2t. Okay. Okay, so we're going to substitute those into our equation for the normal. So we are going to get 4 cos of t minus 2 root 3 cos of 2t. Now 2 root 3 is 2 times 3. So we get minus 6. Lots of cos of 2t minus 1 is equal to 0. Okay. So, what we now need to remember is our trigonometric identity for cos of 2t, which is that cos 2t is cos squared t minus sine squared t. From that, we can get cos 2t is equal to 2 cos squared t minus 1. So our equation is then 4 cos t minus 6 minus 6 times 2 cos squared t, minus 1. So we're going to get minus 12 cos squared of t, add 6, and then we got the minus 1 on the end, so that's all equal to 0. Now we can rearrange this to 12 cos squared t minus 4 cos t, and then we've got, well, up above we would have plus 6 minus 1, which would give us positive 5. So if we've rearranged, we're going to get minus 5 is equal to 0. So we've got a quadratic now. In terms of cos, we can actually factorise this guy. So after a little bit of tinkering, we can write this as 6 cos t minus 5 times 2 cos t plus 1 is equal to 0. So this tells us then either cos t is equal to 5/6 or cos t is minus 1/2. Now that solution on the right is the one that we've been dealing with at point P. If we inverse cos that, we would get 2 pi over 3. So the guy that we are interested in is this chap here. Cos of t is 5/6. So if we know cos of t is equal to 5/6, 6. Well, remember that we know the parametric equations are x is equal to 2 cos t and y is equal to root 3 cos 2t. So, we know that cos of t is 5, 6. So, the x coordinate at point Q, well, that's going to be 2 lots of 5, 6. Which is 10 6 or 5 thirds. And then for the y coordinate, we're going to use the cos of 2t identity again. So we can say that y is root 3 times 2 cos squared of t minus 1. Now again, we know that cos of t is 5, 6. So this is equal to root 3 times, okay, so 5, 6 squared is 25, 36. If we multiply that by 2, that's 25 over 18. So we got 25 eighteenths minus 1. Now 1 is 18 eighteenths. So 25 eighteenths minus 18 eighteenths is 7 eighteenths. So the y coordinate is 7 eighteenths root 3. So finally, the coordinates of Q are 5 thirds and 7 root 3 over 18. Good times. Okay, question 14. So here we have part of the graph of y equals x squared log x over 3 minus 2x plus 5. So we got this shaded region here, S, which is bounded by x equals 1 and x equals 3, the curve C and the x-axis. So we are given this table of corresponding x and y values, where the y values are given to 4 decimal places. We are asked to use the trapezium rule with all the points in the table to work out an estimate for the area, giving our answer to 3 decimal places. Okay, trapezium rule then. Okay, so our trapezium rule looks like this. H over 2, where H is the width of the strip, times y0 plus yn plus 2 lots of y1 plus y2 plus y3 all the way up to yn minus 1. So let's plonk our values in. So h is 0.5 here. So we've got 0.5 over 2 is 0.25 5. Now, y0 is 3, and yn is 2.2958. So we want 3 plus 2.2958. Add 2 lots of all the other y values added together. So 2.3041 and 1.9242 and our final value 1.9089. Okay, check that all in your calculators, and we should get S is roughly equal to 4.393 to 3 decimal places. Cool. Okay, then part B wants us to explain how the trapezium rule could be used to obtain a more accurate estimate for the area. So basically use more strips. However many, or the more strips you use, the more accurate your answer is. So for part B, use more strips. Cool. Okay, then part C wants us to show the exact area of S can be written in the form A over B plus log C, where A, B and C are integers to be found. So, how are we going to do this? Integration. So, the area is the integral between 1 and 3 of x squared log x over 3 minus 2x plus 5 with respect to x. Now, first of all, we're just going to worry about integrating x squared log x over 3. The minus 2x plus 5 bit we can do with our eyes closed. Okay, so to do the integral of x squared log x over 3, we are first of all going to take out that factor of a third, so it's 1/3 the integral of x squared log x with respect to x. Now, to integrate this bad boy, we're going to need to use integration by parts, which is always a good time. So, remember, integration by parts tells us the integral of v times du by dx with respect to x is equal to uv minus the integral of u times dv by dx. So we need to be clever about which function we call which letter. We don't want to be integrating log x. So we're going to say that v is equal to log x. So then dv by dx is 1 over x. So then we're saying du by dx is x squared. So that then means that u is x cubed over 3. Now, I'm going to call this whole integral that we are calculating I. So remember, I is 1/3 the integral of x squared log x with respect to x. So, now we can say I is 1/3 of u times v. So that's x cubed log x over 3 minus the integral of u dv by dx. So that's x cubed over 3 times 1 over x. So that is the integral then of x squared over 3. With respect to x. So that's good because we can now do that integral nice and easily. So I is 1/3 x cubed log x over 3 minus, so x squared integrates to x cubed, but then gets divided by 3, so we get minus x cubed over 9. Okay, so now if we let that factor of a third in, finally we get I is x cubed log x over 9 minus x cubed over 27. So up to there, the only part that we've integrated is x squared log x over 3. We want to integrate the whole function, so s is the integral between 1 and 3 of x squared log x over 3 minus 2x plus 5 with respect to x. So we now know them that we've run out of room. Okay, so we now know then S is, okay, so we've got x cubed log x over 9 minus x cubed over 27 and then when we integrate minus 2x, we're going to get minus x squared, and then when we integrate 5, we get 5x. So there's our integral. We now need to substitute in the values. Okay, nice and slowly then. So when x is 3, x cubed is 27. So the 27 cancels with the 9 and gives us 3 log 3 minus x cubed over 27. It's going to be 27 over 27. So that's minus 1. And then minus 9. And then plus 15. And then in the second bracket, we're going to get minus. So when we put in x equals 1, the log term disappears. It's equal to 0. So that first term, x cubed log x over 9, is 0. So we're going to get minus 1 cubed over 27. So that's minus 1 27th minus 1 squared. So minus 1 and then plus 5. Okay. So this first bracket, we've got 3 log 3 minus 1 minus 9 is minus 10 plus 15 gives us plus 5. And now we got a minus 1 27th, which is add 1 27th minus 1, so plus 1, and then minus 5. Okay, so we've got 3 log 3, so we got 5 plus 1 minus 5, which is 1, and then we're adding 1 27th. So 1 whole is 27 27ths. So add 1 27th, and we've got 28 27ths. Now, finally, by the rules of logs, 3 log 3 can be written as log 3 to the 3. So this is finally log 27 add 28 over 27ths. Good times. Okay, question 15. So we got this lovely curve here. The equation is f of x is 4 sine 2x over e to the root 2 x minus 1. The curve has a maximum at point P and a minimum at point Q, and we want to show that the x coordinates of these points satisfy tan of 2x is equal to root 2. So to do that, we're going to need to differentiate. Stationary points happen where the gradient is equal to 0. So we're going to set our derivative equal to 0 and hope we can get something that looks like this. So we have a function here of the form f of x is equal to u over v. So to differentiate this, we're going to need to use the quotient rule. So df by dx is v u dash minus u v dash all over v squared. So u is 4 sine 2x, so the derivative u dash is 8 cos 2x, and v is e to the root 2x minus 1, so v dash is root 2 e to the root 2x minus 1. So our derivative df by dx is, so it's v times u dash, so it's 8 cos 2x times e to the root 2x minus 1 minus u times v dash, so that's going to be 4 sine 2x times root 2 e to the root 2x minus 1. So I'm going to write that as 4 root 2 sine of 2x times e to the root 2x minus 1. Now that's all over v squared. So that's all over e to the root 2x minus 1 squared. So there is our derivative. Now at the stationary point, the derivative is equal to 0. So if we set df by dx equal to 0, then the first thing we can do is multiply that denominator away. So multiply both sides by e to the root 2x minus 1 squared. Then we're going to get left with 8 cos 2x e to the root 2x minus 1 minus 4 root 2 sine of 2x e to the root 2x minus 1. So the next thing we can do, which is going to make it a lot nicer, is, well, first of all, not forget to set that equal to 0. We also have a common factor of e to the root 2x minus 1. So we're going to divide that away next. So then we are left with 8 cos of 2x minus 4 root 2 sine of 2x is equal to 0. So all of a sudden that looks quite a bit friendlier. Okay, so we want to get this in the form tan of 2x is equal to root 2. So I'm going to add 4 root 2 sine of 2x to both sides. So we then get 8 cos of 2x is equal to 4 root 2 sine of 2x. Now there's a common factor here of 4. Divide that away, then we get 2 cos of 2x is equal to root 2 sine 2x. We need to get a tan in here, so remember tan is sine divided by cos. So I'm now going to divide both sides by cos of 2x. So we're going to get 2 is equal to root 2 tan of 2x. Divide by root 2, we get 2 over root 2 is equal to tan of 2x. And then finally, if we rationalise that denominator, 2 over root 2 is root 2. So root 2 is equal to tan of 2x. So we've done that. Good times. Okay, now for the final part, using our answer to part A, we want to find the x-coordinate of the minimum turning point in the curve with equation y equals f of 2x, first of all. So, remember, this guy, tan of 2x equals root 2, would be the solution for y equals f of x. So, for f of 2x, we want to solve, well, tan of 4x is equal to root 2. So again, because f of x has a solution, tan of 2x is equal to root 2, f of 2x will have a solution of tan of 4x is equal to root 2. So, from that, we get 4x is the inverse tan of root 2, and we're in radians, remember? So, the inverse tan of root 2 is 0.955. Now, if we divide by 4, x is equal to 0.239. Now, what that's giving us, it's giving us the first solution to that equation. So that would be the x-coordinate of the maximum. But we want the x-coordinate of the minimum. So it's going to be the next solution. Now remember, tan has a period of pi when we're talking about radians. So tan of 4x has a period of pi over 4. So the solution that we want is, so the minimum x coordinate is 0.239 add pi over 4, which gives us, if we go to 2 decimal places, 1.02. Okay, and then for part 2 of B, we've got y equals 3 minus 2 f of x. So for this we need to think about what this is doing to the graph. So the minus 2 multiplying the function reflects it and stretches it in the x-axis. So it's going to become twice as high, if you like, but negatively. So it's going to make our graph look something like that. And then when we add 3 to it, what that does, it translates our graph up by 3 places. So it's going to do something like that. So for this guy, the minimum is now here. So the minimum is now the first solution to tan of 2x is equal to root 2. So the minimum is now the first solution. The reason that we are still solving tan of 2x is equal to root 2 is that these transformations, a reflection in the x-axis and then a translation up by 3, do not affect the x-coordinates of the turning points at all. The turning points, as far as x is concerned, are still in the same location. The only difference is they've been reflected and translated in the y direction. So, we now want to solve them. Tan of 2x is equal to root 2. So if we put that into our calculators, remember we're in radians again, so inverse tan of root 2, and we get, if we go to 3 decimal places, 0.955. So 2x is 0.955. 5. 5. So then if we divide by 2 to 3 decimal places, we get x is 0.478. Good times. Okay, there's the paper done, guys. So I'm going to do paper 2 at some point. Really hope this has helped. Let me know. Give us a thumbs up. Get subscribed. Take care. Take it easy.